Hi everybody. I did get multiple requests to do problem 104 from last week. This is in chapter 6. What's nice about doing this is that it's a time-dependent force, which is something we're going to see next week. All right, so it basically says a particle of mass m is located at the origin. So, okay, if it's located at the origin, it is at rest and in equilibrium. So if it's located at the origin, that basically tells me, okay, then my initial position when the, or I could say r, let's say r, because they're using r for position here, because it's a general notation for position. So the initial position when time equals 0 is going to be 0. And then it says it's at rest. So if it's at rest, then the initial velocity at time equals 0 is going to be 0. And then if it's in equilibrium, that means that the acceleration when time equals 0 is equal to 0. Although we won't really need this, but that's good to know. And then it says a time-dependent force of Ft is applied at time t equals 0, and its components are Fx of t is p times t. This means that the x component of the force as a function of time is equal to a constant p multiplied by the time. And then this is the y component as a function of time of the force, and it's equal to a constant n plus another constant q multiplied by t. And then they tell me all those things are constants. It says find the position rt and velocity vt as functions of time t. So we're trying to find the position and velocity as functions of time. And the thing is that because this force is time dependent, I can't use my general or specialized kinematic equations that I could have used if the force was constant. I got to use calculus. I have no choice. A couple things I'm going to bring up. One I'm going to throw off to the side here is that let's see, if I know the position as a function of time and I wanted to get the velocity as a function of time, all I have to do is take the derivative. And then again, if I know the velocity is a function of time and I want to get the acceleration as a function of time, again, I would take the velocity's derivative. That would give me the acceleration. But if I know the acceleration is a function of time and I want to get the velocity as a function of time, I could take the integral. And then if I know the velocity is a function of time, but I want to get the position as a function of time, I could again take the integral. Okay, so last thing I want to just kind of mention briefly here is just to get an intuitive sense about these functions and what they mean. I'm going to use the hat notation here because I know in my solutions I use the bracket notation, so I just wanted to switch things up and use the hat notation just so you can see that. So if I have this particle, again, it starts at rest with a velocity of 0, starts at the origin, and acceleration is 0. Basically, at time equals 0, I have no x force acting here. So no x force whatsoever acting in that direction. However, I do have a y force, because even though when t equals 0 here, that term is going to disappear, n is still the constant. So I'm going to have a force equal to n when t equals 0. But then, when t equals 1, well, then, when t equals 1, I'm going to have a force along x equal to p, or I should say a component of the force along x equal to p. So I would go this way. There will be a force in the x direction, and it'd be equal to p, because t equals 1, so 1 times p is just p. And then in the y direction, I would have, again, t equals 1, so I'd have a force along y that's n plus q. So that means the y component's going to get a little bigger, and this force in the y direction is going to be n plus q. And then when t equals 2, this gets bigger and this gets bigger, etc., etc., etc. So the force is changing as a function of time. All right, let's get to the problem. So whenever I see anything like this that involves forces and they want me to get, well, honestly, anything involving forces, one of my go-tos, the thing that always comes to mind is, well, I know the net forces is equal to the mass times the acceleration, the second law. And in this case, I've got two components to the net force, the x and y component. Now, I know in the past you've seen me drawing them kind of in separate lines. This time, though, I'm going to draw them all on one line. So that's going to give me the x force times x hat plus the y component of the force times y hat is equal to the mass times the acceleration. All right, well, plugging these things in, such as the x component of the force is equal to the constant p multiplied by t x hat plus the y component of the force, which is n plus qt y hat is equal to the mass times the acceleration. And then if I wanted to get the acceleration as a function of time, which is this, all I would need to do is divide everything by the mass. So let's do it. Divide by mass. Divide by mass. So I'm going to simplify this a little bit here. I'm going to get, well, the masses are definitely going to cancel out. I'm going to write the components p over m, or not the components, the constants p over m, and they're being multiplied by t. And that's x hat right there. Plus n over m here. That's just a constant there. Plus, and then the constants q over m multiplied by t. You can write this in any form that you want. This one's the one that's making most sense to me. So y hat, and then that's the acceleration as a function of time. All right, and once again, if I know my acceleration as a function of time, to get the velocity, which is one of the things that this problem is asking me, I just need to take the integral. Let's do it. So to get the velocity as a function of time, it's going to be the integral of the acceleration as a function of time dt. So I'm going to kind of skip a little step here, and that's that if I take the integral, I can just integrate each of these separate parts. See if I can point them out here, here, and here, because they're all being added up, but I can integrate each separate part and then add up the total, because that's one of the properties of integrals that we learned. So, okay, I'm going to pull out these constants, p over m, and then, so for here, for this one, I'm just going to integrate t dt, because I'm integrating as a function of time, so I'm integrating anything with a t in it. This does not have a t in it, so I'm just going to, let's put that in parentheses, hopefully that'll be a little clearer. I'm going to call x hat, and then I'll call this one here, that's going to be n over m. I'm integrating nothing, I'm integrating just constant, so I'm going to integrate the number 1 dt. Plus all this stuff over here, that's going to be the constants q over m and I'm going to integrate t dt. Because again, that's t right there. All right, and then that's in the y hat direction, and there we go. So let's integrate each of these parts really quickly. So my velocity as a function of time is going to be, right, vector arrow there. It's going to be, well, the integral of t is just t squared times a half. And that's going to multiply by p over m, x hat, plus the integral of 1 is just t. So it's going to be t multiplied by n over m. Oh, sorry, I'll throw in the constants here. So plus a constant in the x direction. Always forget that plus c. Plus q over m. The integral of t is just t squared multiplied by a half. And that's going to be plus c in the y direction, y hat. So there we go, there's my velocity as a function of time. But then I can plug in my initial conditions that when time equals 0, the velocity equals 0. And that's the velocity in both the x and the y direction. So let's kind of throw that in there. I know that the velocity when t equals 0 is 0. So that means all this will be 0. So that'll leave me with just cx, x hat direction, plus this will be 0, and this will be 0, so that'll leave me with cy in the y hat direction. And because this velocity is 0 in both the x and the y direction, that basically just tells me cx equals 0 and cy equals 0. So lastly, just to get my velocity as a function of time without the constants, it's going to be, I'll simplify some of these here, that's going to be p over 2m t squared x hat plus this term right here, which is n over m times t plus q over 2m t squared. This is now 0. So that's going to be y hat. And there's my velocity as a function of time. Awesome. Oh, but now I also need to get the position as a function of time. And hey, to get the position as a function, if I got the velocity as a function of time and I want to get the position, well, all I need to do is, I got to take the integral again. Let's do it. Woo, integral. All right. So let's see. To get the position as a function of time, write that as a velocity vector. Well, that's going to be the integral of the velocity as a function of time, dt. And I got this. So let's see. Again, I'll split this up into its parts. I'll take the components, throw them on the outside, 2p over 2m. And I'm going to integrate time, t squared, dt, all that, x hat, plus, now this term now has a time variable in it, so it's going to be n over m. And I take the integral of t dt plus this term right here, which is the constants q over 2m. And then I'll take the integral of t squared dt. And all that's in the y hat direction. All right, let's take these integrals. So these are all just constants. The integral of t squared is going to be, so all this is the position as a function of time. That's going to be, the integral of t squared is t cubed times a third. And that's p over 2m plus a constant. Just to show it'll be different from the other constants, I'll call it k in the x direction. And all that is in the x hat direction. Plus integral of t is just going to be t squared times a half. All that's going to be multiplied by n over m. And so there we go. Plus the integral of t squared, as we just said before, is t cubed times a third. And we got to include those constants, q over 2m. And then we will do plus k in the y direction, y hat. All right, so again, we can get rid of some of these constants, or we can establish some of these constants by giving our initial condition that when the time equals 0, the initial position is 0 because it's at the origin. So let's see, that's going to be when time equals 0, r equals 0 in the y direction and the x direction. So this is 0 in the y direction and the x direction. So it's going to be p over 2, or well, I can just kind of see here, if t equals 0 here, it's going to cancel all this stuff out. So it's just going to give me kx. And then again, if t equals 0, all this is going to go. all this is going to go, leaving me with just ky. And so if the position is 0 in the x direction and in the y direction, that means kx equals 0 and ky equals 0. Well then, I can get my final position as a not a final position, but my equation, my position as a function of time. So it's just going to be equal to, just simplifying here, it's going to be p over 6m t cubed. Kx is 0. So we got x hat here, plus all this stuff, which is n over 2m t squared, plus all this stuff. So it's going to be q over 6m t cubed. And then ky is 0 again, so it's just going to be y hat. And there is my position as a function of time. So once you know to take the integral, it becomes a little, the difficult thing I think is categorizing everything, making sure that everything is kept separate. And but yeah, hopefully those are integrals you're able to do, and hopefully that helps. All right, see you guys. Bye.